Let's start with a basic truth of computer science. Hardware, algorithms, and lines of code do not possess a conscience. The silicon inside a processor cannot decide what is right or wrong. The moral complexities we face in technology are strictly a product of how human beings choose to apply these systems. A database architecture designed to store user profiles efficiently can just as easily be weaponized to harvest massive amounts of private data. The code remains identical. The human intent dictates the outcome. This gap between what a system can do and what it should do is governed by cyber ethics. These are the specific moral principles required to guide human behavior when operating within digital environments. As developers and security professionals, we have to stop blaming the machine for poor outcomes and take ultimate responsibility for the moral architecture we design. When dealing with algorithmic dilemmas, relying on your gut feeling is dangerous. Subjective morality does not scale securely across complex global networks. Computer science is built on strict mathematical logic, yet human moral decisions have historically been ambiguous and highly debatable. To bridge that gap, ethical dilemmas must be treated as solvable, systems-level problems. We achieve this by applying structured analytical methodologies. A functionally secure computing environment that protects data perfectly is still a deeply flawed system if its core design cannot be ethically justified. As computing networks evolved, the potential impact of a single action multiplied. In cybersecurity, we track this expanding threat as a widening digital blast radius. In the early computing era, from the 1960s to the 1980s, computer misuse was highly localized. The ethical concerns were strictly limited because these massive mainframe machines were isolated and accessible to very few users. When the internet expansion hit in the 90s and 2000s, personal connectivity took off. This standalone desktop represents the period where privacy concerns and digital identity theft scaled to reach the general public. Today, in the modern era, ubiquitous computing is powered by dense, scalable cloud data centers. The stakes here involve AI ethics, massive data aggregation, and global cyber warfare. The primary threats we confront now are data breaches, identity theft, cyberbullying, and systemic algorithmic bias. Because the technological blast radius is now global, a single programmer making a poor ethical choice can instantly impact millions of individuals and compromise entire governments. To process these variables, we translate abstract philosophical concepts into recognizable logic gates. Think of a raw ethical dilemma passing through three distinct processing nodes. The first node is utilitarianism. This is an outcome-focused function that calculates the greatest possible good for the greatest number of users, weighing overall benefit directly against potential harm. The second node operates on deontology. This is a rule-focused function, requiring absolute adherence to predefined duties and privacy obligations. It evaluates the rules themselves, regardless of the calculated outcome. The final node is virtue ethics. This is a character-focused function that evaluates the internal integrity of the system design itself, prioritizing structural fairness and the mitigation of systemic bias. Pass a single ethical issue through these three different logical lenses, and you will often generate distinct yet logically defensible outputs. This chart outlines the 5-step methodological framework. It serves as the mandatory operating procedure for professionals facing dilemmas. Steps 1 and 2 require you to identify the technical issue and map out every affected stakeholder. Step 3 demands that you quantify and evaluate the potential physical, digital, and emotional consequences on those specific stakeholders. Finally, steps 4 and 5 require passing those variables through your chosen ethical framework to compile a justified final system decision. Executing this structured methodology is not an optional academic exercise. It is a critical technical competency required for cybersecurity professionals. Let's apply this compiled methodology to deconstruct real-world architectures, where the code functioned perfectly, but the system failed ethically. In the Cambridge Analytica data privacy violation, the system successfully harvested millions of user profiles without explicit consent. Accountability for this architecture rests at the highest levels of these data platforms. A utilitarian might attempt to debate the data's utility for targeted messaging. However, deontology definitively flags the action as a systemic violation because it breaks the absolute rule of user consent. We see similar failures in AI bias within modern hiring systems, where algorithms actively discriminate against specific demographics during the filtering process. Evaluated through virtue ethics, training an algorithm on biased historical datasets violates the core principle of systemic fairness, regardless of how efficiently it sorts resumes. In both massive case studies, the systems functioned exactly as programmed. They processed the inputs and delivered the outputs. This proves that perfectly functional code does not equal ethical code. The ultimate test for any computer scientist is navigating competing, mutually exclusive system imperatives where no perfect technical answer exists. This brings us to the central discussion question for the upcoming class. Is it ethical for governments to monitor citizens' online activities for national security? The utilitarian argument supports government surveillance by focusing on optimizing the broader security benefits, arguing that protecting the entire nation outweighs individual discomfort. The opposing deontological argument rejects surveillance completely, citing the strict violation of an individual citizen's right to digital privacy. Because there is no simple mathematical resolution to this tension, the rigorous application of a chosen framework is the only reliable way to justify the final system architecture. For your class activity, you must evaluate this dilemma and choose a definitive position. Stating a preference is insufficient. You are required to explicitly justify your position by running the scenario through the 5-step decision-making methodology. Remember, cyber ethics provides the framework that guides human behavior in digital environments. As you prepare to build increasingly complex systems at UUM and in your future careers, your structured ethical reasoning must be just as robust as your code.